Alright guys, so I realized in the last video the video capture was not keeping up with my voice. So I'm going to pick back up on this question where we left off. I'm having some issues with that notebook program, so I'm going to switch over to just writing in the PowerPoint like I did last semester if you were with me. This is actually my fourth attempt trying to record this for you guys. Last time I got all the way to the end and I lost the footage, so hopefully we'll have some better luck with this and I'll be able to get this up to you guys. But just so if you notice the format change, that's why. I can still I'll still upload those solutions for you guys. I'll just have to rewrite them in the notebook program. That's no big deal. Hopefully between now and next week I'll be able to find a solution for that. So let's just pick up. So hopefully you watched the last video, so you kind of followed me in picking out all the information. So let's just start straight from actually setting up the question. Okay, so we know this is a Henry law problem, so we know that our solubility of our gas is equal to our constant, so our Henry's law constant, times the partial pressure of our gas. So for this question, if I want to know S of O2, that will be equal to our constant, so 1.66 times 10 to the minus 6, and this has units of molarity over millimeters of mercury. And we're going to say times the partial pressure of the oxygen. Okay, so in this case they tell us that it is, sorry, this is why I like using that notebook program a lot better. So the partial pressure of oxygen, they tell us 160 millimeters of mercury. Okay, so now you just have to go through and do the multiplication here. And from that I come up with 2.66 times 10 to the minus 6th. And now to check our units, millimeters of mercury cancel with millimeters of mercury, so we're left just molarity. So in this problem they gave us our constant in millimeters of mercury, and they gave us our concentration or our partial pressure in millimeters of mercury. So in this particular case we can just multiply them directly and not have to worry about converting the units. But if for some reason they gave you different units, you need to convert them so that they're the same. Usually you will convert your unit to match your constant, but that's not necessarily true. Okay, but we need to go one more step. So it wants to know how many grams of O2 per liter of water. So right now we're molarity, and remember that we can rewrite molarity as being moles over liters. Okay, so we want to get to grams of oxygen. So how can we do that? So if we just take our 2.66 times 10 to the minus 6, and let's write this with dimensional analysis. So moles over 1 liter. Okay, so what do we need to go from moles to grams? Well, we need our molar mass. So we know that for oxygen, our molar mass will be 32 grams are in 1 mole. Okay, so our moles will cancel with our moles, and this answer will give us grams per liter. So if we do this math, we end up with 8.5 times 10 to the minus 3 grams per liter, and that's the answer we wanted. Okay, so this is our, or the units we wanted, so this is our final answer. Okay, so that's the part of the solution you guys didn't see in the last part. Okay, so hopefully that wasn't too bad. It's pretty much just plugging in the numbers once you know where they go. Okay, so this next section we will cover some units for concentration, so different ways to express concentration. So there's a couple ways we can do this. So one is qualitative, meaning it's sort of vague terms where we don't care so much about exact quantities. Okay, so I can say a solution is diluted, or it's the dilute solution, or I could say something is a concentrated solution. An example of a diluted solution would be maybe if I take like 1 milliliter of HCl and I dilute that into maybe a liter of water. Okay, so that would be a dilute acid solution. Whereas a concentrated solution, this might be something like you make a stock solution. Say you dissolve 100 grams of sodium hydroxide into whatever volume of a concentrated volume of water. So say 100 mil. I don't know if that will really dissolve. Probably not. And then from there, you could take small portions and dilute them. So that would be like a stock solution or a concentrated solution. But if we want to be more specific, well, with the qualitative, I could ask you, how concentrated is that solution? And you would say, oh, it's dilute, it won't hurt you. So those are the kind of ways we would use these qualitative factors. But if we want to be more specific and we actually want to do calculations with our numbers, we need what is quantitative methods. Okay, so quantitative-based units. And these are things like mass-based units or mole-based units. So I could have mass percent, parts per million, parts per billion. Or if I was doing mole-based, those are mass-based. If I wanted to do mole-based, I could have mole fraction, I could have molarity, or I could have molality. Okay, we're going to take a look at each of these. But these would be more specific units. So if I wanted to calculate, how much volume of this solution do I need to do this reaction with, if I know the molarity, or I know the molality, or I know the mass percent, then I can figure out how much of it I need to use. So it's a lot more specific than just saying, oh, it's concentrated or not concentrated. So the first one we'll look at is mass percent. So this is just the mass of the solute over the total mass of the solution. So remember when you're when you're trying to figure out percentages, you always want to do the part over the whole. And then, of course, times 100. That's how you get a percentage. And it doesn't matter what you're taking a percentage of or a fraction of. This will always be the same way. So notice here, we have the mass of the solute over the total mass of the solution. So the total mass means not only the mass of the solvent, but also the mass of the solute. Okay, and these need to be in the same unit. So if one's in kilograms, they both need to be in kilograms. Or if one's in grams, they both should be in grams. Okay, and down below they have a note for us that says if we have a solution that is 5.5% by mass of solute A, that means that for every 100 grams of solution, 5.5 grams of that is solute. Okay, and we'll look at ways to use that. So suppose we had a sample of 0.892 grams of potassium chloride is dissolved in 55.6 grams of water. They want to know what is the mass percent of KCl in the solution. Okay, so the way I'll find this is first I need to know what a mass percent is. Okay, so we know it's the mass of the solute in the solution over the total mass of the solution times 100. So I need to plug in my numbers now. So the mass of the solute, so just the mass of the KCl, over, and notice here, over the mass of the KCl plus the mass of the water. So it's not just the mass of the water, it's not just the mass of the KCl, but it's both together. And then we multiply that by 100, and that will give us our mass percent. Okay, so our mass percent in this case would be 1.61%. Okay, so here's a problem for you to try. Sorry about the clanging. So it says assume you have a solution that is 5.75% by weight of lithium chloride, and it wants to know what mass of solution in grams will contain 1.6 grams of lithium chloride. Okay, so give this a try, see what answer you come up with, and then restart the video, and we will go over it together. So I'll give you a couple seconds to pause. Okay, so let's take a look at this one. So this time, we want to know what is the actual mass of the solution. So they gave us a percentage this time, and they want to know what's the mass of the solution. Okay, so remember my formula. So my percent is equal to the mass of the solute over the mass of the solution. Okay. So we can rearrange this equation to give us just the mass of the solution. So let's say mass percent. Okay, so let's rearrange this. So the first thing we'll do, multiply both sides by the mass of the solution. Okay, so this will cancel, and now just say times mass of the solution. Okay, so now I'm left with mass of the solution times the mass percent is equal to the mass of the solute. Okay, so now, but what I'm after is the mass of the solution, right? So I'll divide this whole thing by the mass percent on both sides. Okay, so this will cancel. So what I'm left with is the mass of the solution is equal to the mass of the solute over the mass percent. So now all we have to do is plug in our numbers. So this becomes equal to 1.60 grams of lithium chloride over, now since we're using a decimal in math, excuse me, a percentage in math, we need to convert this to a decimal. So we need to say, instead of 5.75, we'll say 0.0575. So just convert your percentage to a decimal. Okay, and if you do this math, and you run, so just divide those two numbers, you'll end up with 27.83 grams. And how many sig figs do we have? We only have 3. So this will be approximately equal to 27.8 grams. Okay, and that's the mass of our solution. Okay, again, and I will include this work as a PDF for you on the Blackboard. I have actually, funny enough, I have them written out already from my previous attempt to do this video. So I will go ahead and include this for you. So let's move on. So the next one is part per million and parts per billion. Okay, so for parts per million, it's just the mass of the solute in the solution over the total mass, so very much like mass percent. So the big difference here that makes it not just a mass percent is instead of multiplying by 100, we multiply by 10 to the 6th, which is the same as saying milligrams per liter. Or I can have parts per billion, okay, which is essentially the same thing, except now we multiply by 10 to the 9. So these are our two major differences. That makes it either parts per billion or parts per million. Okay, and again, notice that the masses have to be in the same unit. Okay, and then parts per billion is the same as saying micrograms per liter. Okay, so sometimes it's easier to figure things out by just converting to milligrams per liter and knowing that's parts per billion, or parts per million, excuse me. Sometimes it's easier to actually multiply by 10 to the 6th. So just depending on the situation, one of these might have advantages over the other. Okay, so here's a problem you can work out, and I'm going to let you try this one on your own. And once again, I will post the solution for you. But it says you dissolve 560 grams of NaHSO4, and they give you the molar mass, in a swimming pool that contains 4.5 times 10 to the 5th liters of water. So what is the sodium concentration in parts per million and in parts per billion? Okay, so give this one a try, and I will post the solution for you, but see what you come up with on this. So it's not so different than just a regular mass percent question. Okay, so see what you can come up with. One thing I will let you know is that for every mole of this, notice we're looking for the moles of sodium. So for every moles of our sodium-containing compound, it only produces 1 ion of sodium. Okay, so notice we're looking for parts per million and parts per billion. So take that into account when you're finding your answer. And I will, again, post the answer for you. Next one, mole fraction. So this is equal to the moles of solute A over the total moles of solution. So now we're looking at a mole-based unit. Okay, and we use the symbol chi, or x, for mole fraction. And again, it's just the moles of solute A over the total moles. So really no different than the fraction of anything else. So the part over the whole. Remember I said part over the whole. So anytime you're dealing with percentages or fractions, that's really all you're doing. Okay, so in this case we need molar quantities, okay, for the solute and for the solvent. So that's our big difference here. We're no longer talking about mass only. We actually have to talk about the moles. Okay, the molarity we already know, but remember it's moles of solute A over liters of solution, so moles per liter. That's probably the one we've used the most so far. Okay, then the last one, molality. So this is the moles of the solute over the kilograms of solvent. So notice this is very key here. So kilograms of the solvent, not of the solution, not of the solute, but only of the solvent, and it wants it in kilograms. So just like up here, we want this in liters. Here we actually want the mass of the solvent in kilograms, because that's our unit. So pay close attention to that when you're solving things. And this last one we will use in the last section of this chapter when we're dealing with colligative properties, lowercase m. That's actually a pretty fun section, I think, so we'll get to there eventually. Okay, and then we can note here that molarity is temperature dependent. That's mainly because of the fluctuation of the volume due to temperature. Okay, so here's one for us to kind of an example problem. Okay, so it says, assuming that seawater is an aqueous solution of sodium chloride, it wants to know what is the molarity, and it tells you the density of the seawater is 1.025 grams per milliliter at 20 degrees C, and it tells us the concentration is 3.5 mass percent. Okay, so we're looking to solve for molarity. We have a density, and we have a concentration in mass percent. Notice one thing we're missing in this problem. They don't tell us a volume. So what will we do? How can we solve this problem if they don't tell us a mass or a volume? They only tell us a mass percent. So what can we do? Well, what we have to do is we have to make an assumption. So we'll assume that we have 100 grams of solution. Okay, and from there, we can calculate our volume. So since we have a density, if we assume 100 grams of solution, and we can make this assumption as long as we stick with it, then we can calculate the volume. Okay, so if we have 100 grams, we have a density. Okay, so in this case, we want to divide by density so that grams cancel. And we'll be left with milliliters in this case, but we want liters because that'll help us out to calculate molarity. So we just convert milliliters to liters, and we find this as the volume. Okay, so what else do we need? We need moles, right? For molarity, we need moles per liter. So now we have a mass percent, we have a volume, and we also have a mass of solution. Okay, so what can we do now? So again, assuming that same 100 gram sample, we can calculate the mass of sodium chloride. Okay, so we just take 3.5, and we know that's equal to that there's 3.5 grams of sodium chloride per every 100 grams of solution. Okay, so if we multiply these numbers, so for 100 grams of solution, we know there's 3.5 grams for every 100 grams. Okay, so in other words, we have 3.5 grams of sodium chloride. So if we didn't assume we were using a 100 gram solution, this step would be a lot more important. But since these just cancel, essentially we didn't really do anything. But this is essentially, this 3.5, this is a conversion factor. Okay, it's a self-made conversion factor. Okay, and then whatever, so if we assumed, for instance, 1,000 gram solution, then we would have 35 grams of sodium chloride. So that's the difference. Okay, so don't always just assume that whatever grams, whatever the percent is, that's the number of grams, unless you're using 100 gram solution. Okay, so all that's left now is to find the mass of sodium chloride and convert it to moles. Okay, so we know that there's 3.5 grams of sodium chloride, which we just found, and we want to use the molar mass of sodium chloride to convert to moles, so not too bad here. So grams cancel with grams, and notice we're using 1 over the molar mass, so normally molar mass is grams per mole. We flipped it here so that our dimensional analysis works, and we're left with moles. Okay, so last step just calculate the molarity. So we know that molarity is equal to moles per liter. So all you have to do is plug in the number of moles we found divided by the volume we found and liters, and that will give us molarity. Okay, so what if we want to know the molality of a solution prepared by dissolving 0.385 grams of cholesterol, and they give us a formula there, and 40 grams of chloroform. Okay, so we have a nonpolar solvent, and we're dissolving some fat, cholesterol, and they want to know what's the molality. So how can we go about this? So if we remember correctly, we need a couple things for molality. We need moles, and we need kilograms of solvent. Okay, so moles of solute, kilograms of solvent. So the first thing, let's just convert the mass of cholesterol to moles, because that's what we need. Okay, they give us a chemical formula here, so we have to convert that chemical formula to a molar mass. Okay, so 386 is our molar mass. Okay, so take your 0.385 grams of cholesterol, divide by the molar mass to get to moles. Okay, what else do we need now? Now we need to know the actual mass of the solution in kilograms. So they gave us the mass of chloroform, but it's in grams, so we'll convert to kilograms. So divide by 1,000, easy enough. Okay, and lastly, to find the molality, okay, what do we need to do? We need to divide the moles by the kilograms of solvent. Okay, easy enough. Plug that in your calculator, and you come up with a molality. And remember, this is little m. Okay, so molarity is big M, molality is little m. Very similar sounding words, very similar symbols, but very different quantities. And there's some flowcharts here for you that you can look at on your own. I generally don't go over those. Some people get a little more confused by them, so I kind of skip over them. Okay, so here we have a 0.75 molar solution of sulfuric acid, and they give us a molar mass there. And it's in water, and it has a density of 1.046 grams per milliliter at 20 degrees C. And it wants to know, what is the concentration of the solution in molality, mole fraction, and mass percent? Okay, they give us some notes here. So for molality, we need moles of sulfuric acid and the mass of the solvent. For mole fraction, we need moles of both. And then finally, for mass percent, we need the mass of both. Okay, so let's start out by just getting the quantities that we need. Okay, so for molality, we need mass and we need moles. So what do they give us? They give us molarity, they give us a density. Okay, but they don't give us a mass. And they don't give us a volume. So what do we have to do in this case? Once again, we have to make an assumption. Okay, so we make the assumption that we're using 1 liter of solution. Okay, so we can calculate the moles and mass of sulfuric acid in 1 liters of solution and the mass of 1 liters of solution, because we have the density and we have the molarity. Okay, so with those two things, if we just assume a volume, and as long as we can stay consistent with our assumption, we can do this, just like we did before with the 100 grams. So I know sometimes it's hard to know when to do this, but this is a situation where we need to do this, because without this assumption, you can't solve the problem. Okay, so let's just find the quantities that we need. Okay, so first let's find the moles of sulfuric acid. So we have a 1 liter solution, and they tell us we have a 0.75 molar solution, so that's moles over liters. Okay, so we just multiply our volume times our molarity. Okay, so our units here will cancel. And we end up with 0.750 moles of sulfuric acid. Cool. So we have the first thing for our molality, so we can cross this one off. Now what do we need? We need the mass of the solvent. Okay, so first let's find the mass of sulfuric acid. So that's just simple as converting moles to grams. So go through your molar mass, convert moles to grams. And why do we do that? So we want the mass of the solvent, but we just found the mass of sulfuric acid. Well, if 73.6 grams of the solution on sulfuric acid, the rest of the solution has to be the solvent. Okay, so we can find the mass of the total solution since they gave us a density. Okay, so just go through from volume to density. Use the density to go to grams to get the mass of the solution. So use our assumed 1 liter of solution, use the density to get to mass. Okay, so our total solution has a mass 1,046 grams. Okay, but 73.6 grams of that is our sulfuric acid. So if we take the difference between those two, we'll get the mass of just the solvent. Okay, so if we go back, now we have the mass of solvent. Okay, next we need the mole fraction. So we need the moles of sulfuric acid, which we found here. Okay, so we can cross that out. But now we need the moles of water. Okay, so we know the mass of the water. So if we go through the molar mass, that will tell us the moles. Okay, so we can come back, and now we have the moles of water. Now what do we need? We need the mass of sulfuric acid. Well, we have that here. Okay, check. And we already found the mass of the solution, so that's here. Okay, boom. So now we have everything we need to solve the actual problem. Okay, so now all we have to do is plug into our formulas. So we know the molality is moles of solute over kilograms of solvent. So just plug your numbers in, divide, easy. Okay, remember that your unit is a little m. Next one, mole fraction. Remember, mole fraction is the part over the whole. Okay, so just add the moles of sulfuric acid to the moles of water, and then divide the moles of sulfuric acid by that number. Okay, and this would end up being unitless. Okay, since moles would cancel with moles. And lastly, determine the mass percent of sulfuric acid. Okay, so just determining the mass percent of sulfuric acid, we want to know the mass of sulfuric acid over the mass of the solution times 100. So take the numbers we got, plug them in, times 100, boom, 7%, roughly. Okay, and that's it. So once you know all the quantities, it's just plugging it into the formulas. And it's good to understand that those units are they're not just units, you know, they actually have a formula behind them. Okay, so you can use them to actually calculate certain things like this. Okay, so let's give this one a try. So it says a solution is made by dissolving 5 grams of toluene, and they give you a formula and a molar weight there, in 225 grams of benzene. Okay, so they're saying we're dissolving a small amount of toluene in a large amount of benzene. Okay, and they give us a formula, and they give us a molar mass, and they tell us the density of the solution. They want us to calculate the molarity and the molality, and then lastly they want to know what the mole fraction is. Okay, so give this one a try. So it's just like the last one we did. So figure out what it is you need and what it is you're missing. Okay, convert your units and then plug into your formulas. Okay, so I've got a lot to fit in this small little area, so I will do my best here. Okay, so we want to know the molarity, the molality, and we want to know the mole fraction. So for molarity, we need to know, molarity, we need to know the moles of solute over the liters of the solution. Okay, or we could say of the solvent. Let's say of the solution. Okay, so for molality, we need to know the moles of the solute over kilograms of solvent. Okay, and then for mole fraction, we need to know moles solute over total moles of the solution. Okay, so what do we have so far? We have the mass of the solvent. Okay, that's actually perfect. So we know the mass of the solvent, which is benzene, so we can knock that one off. What else do we know? Anything else? Okay, so we have to actually figure this out then. Okay, so we know the total mass of the solution. Okay, what we need to find the total moles, and we need to find the moles of solute and the volume of the solution. Okay, so first let's calculate the number of moles of our toluene. Okay, so we'll take our 5 grams of toluene. I'm going to try to make those a little bit neater for the sake of space. So 5 grams of toluene. Let's just convert that to moles. So in 1 mole toluene, there are 92 grams. And I'm just going to use 2 sig figs since that's our limiting factor anyway. Okay. So if we divide 5 by 92, you end up with, you end up with 5.43 times 10 to the minus 2 moles. Okay, so that's moles of benzene. I'm just going to write of bin to save space. Okay, so now we know the moles of the solute. So that's here and here. Good. So that crosses off the top 3 on all of them. Okay, now we need to know the total volume of the solution. Okay, so how can we figure that out? So we need to find the total mass of the solution. Okay, so that would be 225 plus 5 grams. So 5.0 actually. So our total mass of the solution would be 230 grams of the solution, which is actually one of the things we need to know. Okay. Oh no, we already knew the mass of the solvent. Never mind. Okay, but we do need to know the volume. Okay, and we want to know it in liters. Okay, so we'll use our density to go from 230 grams to actually to volume. So there's 0.876 grams per milliliter in this solution. Okay, so we're going to say for every 1 ml, there's 0.876 grams. Okay, and that will give us our volume. That will give us our volume in milliliters. So this gives us 262.56 milliliters. So we'll have to convert that to liters whenever we want to use it. Okay, so now we can calculate. So we have liters of solution. The only thing we're missing now is the total moles. Okay, so how do we find the moles of the solution? So first, we know the moles of benzene. So we just need to find the moles. I'm sorry, we know the moles of toluene. I said that backwards before. This should be the moles of toluene. Okay, because that's our smaller number. That's our solute. Okay, what we need to know now is the moles of our solvent, which is the 225 grams. Okay, so the moles of our solvent, I'm going to try to write it real small over here in the corner. I'm so sorry. That's really the only space we have left. 225 grams, and just use our molar mass. So for every 1 mole, there's there's 78 grams. Okay, so this gives me, okay, so 225 divided by 78 gives me 2.88 moles. Okay, so our total moles, so if we just add 5.43 e to the minus 2, so we end up with total moles equal to 2.94 moles. Okay, so that's the moles of our solution. So now we know everything. Okay, so now all we have to do is plug in. So our molarity will be equal to, okay, we need the moles of the solute. Okay, so that was our toluene, so 5.43 times 10 to the minus 2 moles. And then what was our volume? Did we calculate our volume yet? Yeah, we did. It was up top somewhere. Okay, yeah, oh yeah, here's our volume. Okay, so we just need to convert that to liters, so that would be 0.2625. So 2626, and that's probably way too many sig figs, but we'll stick with it for now. Okay, so our molarity ultimately becomes 0.207 moles per liter. Oh, that's supposed to be moles, not big M. Let's just write big M. Okay, so that's one answer. And we would probably want to round that to just 2 sig figs, so 0.21 molarity. That's probably a better answer. Sorry, I know this is kind of tiny. I will write this out again for you, though. Make it bigger. Our molality, so little m. So moles of the solute, so again, 5.43 times 10 to the minus 2 over kilograms of solvent. Okay, so they gave us a mass of solvent, so we just have to convert it to kilograms, so 0.225 kilograms. So little m is 2.41 or 0.241, 0.241 little m. Okay, and then lastly, I'm going to erase this top section just because there's nowhere else to write. And remember, our mole fraction is our moles of solute. Okay, so 5.43 times 10 to the minus 2 moles over our total moles, which is 2.94. Okay, so our mole fraction will end up being, I'm kind of going to write this sideways, I'm sorry for that. Okay, so our actual mole fraction is 5.43 e to the minus 2 divided by 2.94. So I get a mole fraction of 0.018. Okay, so here's our mole fraction, here's our molality, and there's our molarity. Okay, so hopefully you're seeing that these are not really that difficult of problem. They're a little bit time consuming, but not overly difficult. Okay, so the last thing here is just a summary of these units. So I'll let you kind of go over this, but this would all be good to know. There's some advantages and disadvantages of each different unit, but the main thing is I would like you to know how to use the unit, what's its definition, what is it used for, and how to calculate it. Okay, so I'm going to end this video here, and when we start back again, we will start with colligative properties.